from hotter to colder, that means that the final temperature will be lower than the initial temperature. Therefore, Q will end up being negative. And what happened is it put off heat. It gave off heat. Therefore, it's going to be a negative Q. Okay, so let's talk about thermal energy transfer. When two objects at different temperatures are placed in contact, heat flows from the material at a higher temperature to the material at a lower temperature. The amount of heat energy lost in the hot material equals the amount of energy or amount of heat gained by the cold material. If we define one substance as a system and the other as the surroundings, we can qualify the heat exchange as the Q of the system equals the Q of the surroundings. That means heat energy lost by the hot materials equals the amount of energy gained by the cold material. Okay, so the heat lost is going to be put off, and then the heat is going to be gained by the cold material. So a block of metal at 55 degrees Celsius is submerged in water initially at 25 degrees Celsius. Okay, so we're talking about that drawing on the previous page. Here's our water. Here's our metal. And it says the block of metal is 55 degrees Celsius. 55 degrees Celsius. And the water is 25 degrees Celsius. Thermal energy transfers heat from the metal to the water. The exact temperature change depends on the following. It depends on the mass of the metal, the mass of the water, and the specific heat capacities of both the metal and the water. So the metal becomes cooler and the water becomes warmer until the two substances reach the same temperature. Remember, this is called thermal equilibrium. Notice that one is gaining the heat is negative and one that's losing the heat is positive. So the metal is losing the heat, therefore it's positive. The water is gaining the heat, therefore it's negative. Okay, so we take into account the mass of the metal, the specific heat of the metal, and the change in temperature of the metal. That's going to equal the negative mass of the water, specific heat of the water, and the change in temperature of the water. So here's an example. Here's a problem. It says a 32.5 gram cube of aluminum, initially at 45.8 degrees Celsius. So the aluminum is initially at 48.5 degrees Celsius is submerged into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Assume that the aluminum and the water are thermally isolated from everything else. So what's happening is the heat is being transferred from the aluminum to the water. Therefore, the aluminum is going to be positive and the water is going to be negative. So you're given masses of aluminum and water and their initial temperatures. You are asked to find the final temperature. Okay, so the heat lost by aluminum equals the heat gained by water. Use the relationship between Q and change in temperature and the given variables to find the relationship between the change in temperature of aluminum and the change in temperature of water. Use the relationship between the change in temperature of aluminum and change in temperature of water that you just found, along with the initial temperatures of the aluminum and the water, to determine the final temperature. Note that at thermal equilibrium, the final temperature of the aluminum and the water is the same. Okay, so here we're going to use that formula. We got the mass of aluminum, specific heat of aluminum. Now remember that change in temperature means the final temperature minus the initial. So what we're trying to find is this final temperature, and it's going to be the same because they're both the same. They're at chemical equilibrium. So the specific heat of water is 4.18 joules per gram degree Celsius, and the specific heat of aluminum is 0.903 joules per gram degree Celsius. Okay, and so we solve for that. So it says substitute the initial temperatures of aluminum and water into the relationship from the previous step and solve for the expression. Okay, so here we got the mass of the aluminum, the specific heat of the aluminum, and the change in temperature of aluminum. Now notice that what they did is they solved for the change in temperature of aluminum. And that's going to equal the negative 14.998 times the change in temperature of water. So now what we can do is change this change in temperature of aluminum as the temperature final minus the temperature initial. Now you can do all of this at once, or you can do it in two separate ways. I'd like to do it in two separate ways just because it's a lot easier to deal with all these minus signs and such. And so the temperature final equals the negative 14.988 times the temperature final plus the 14.988 times the temperature initial of water plus the temperature initial of aluminum. So what we can do is keep solving for the final temperature. So they finally plug these in. There's the 14.988, that's what we got here, times the 15.4 degrees Celsius. That's what that's the initial temperature of the water and the initial temperature of the aluminum. Divided by 15.988. Okay, and that'll give us 17.3 degrees Celsius. Okay, and it says the units degrees Celsius are correct. The final temperature of the mixture is closer to the initial temperature of the water than the aluminum. This makes sense for two reasons. Water has a higher specific heat capacity than aluminum, and there is more water than aluminum. Because aluminum loses the same amount of heat that is gained by the water, it is greater mass and specific heat capacity of water make the temperature change in water less than the temperature change in the aluminum. Okay, let's talk about pressure volume work. So let's kind of shift gears from heat to pressure volume work. PV work is work caused by a volume change against an external pressure. So we have seen that energy transfer between a system and its surroundings can occur via heat or work. We just calculated the heat associated observed with temperature change. Now we turn to calculating the work associated with an observed volume change. Although the chemical reaction can do several different types of work, for now we limit our discussion to pressure volume work. We have already defined work as a force acting through a distance. Pressure volume work occurs when the force is caused by a volume change against the external pressure. So when gases expand, the change in volume is positive, but the system is doing work on the surroundings, so the work of the gas is negative. As long as the external pressure is kept constant, the work of the gas equals the external pressure times the change in volume of the gas. Therefore, the work is negative P change in V. So it says, so the work caused by the expansion of volume is negative of the pressure that the volume expands against, multiplied by the change in volume that occurs during the expansion. The units of the work obtained by using this equation are those of pressure, usually atm, multiplied by the volume, usually liters. To convert liters per atm and joules, we use the conversion factor that there are 101.3 joules in 1 atm per liter. Okay, so it's a negative. The reason that it is negative is because the system is doing work on the surroundings. So the W is negative. Okay, the change in V is positive. This is why it's positive, because the gases expand. But the system is doing work, therefore the overall it's negative. So it says, to inflate a balloon, you must do pressure volume work on these surroundings. If you inflate a balloon from a volume of 0.1 liters to 1.85 liters against the external pressure of 1 atm, how much work is done in joules? So we're given initial volume, we're given final volume, and we're given pressure, the external pressure. And we're trying to find work. So the equation W equals negative P, external change in V, specifies the amount of work done during a volume change against the external pressure. Okay, so to solve the problem, we substitute in the values we're given. So the change in volume, we first find the change in volume. That'll give us 1.75 liters. So work equals the negative. Remember, it's negative because work is being done by the system. Pressure, and EXT means external. So the external pressure, the pressure outside of the balloon. So what's happening is this balloon is expanding and it's doing work against the outside pressure. Okay, so the outside pressure is that 1 atm, and the change in volume is 1.75 because we did 1.85 minus 0.1, that's 1.75. And so the work is going to be 1.75 liters of ATM. Now we're going to convert the units, liters of ATM, to joules using that 101.3, and that gives us negative 177 joules. The units joules are correct for work. The sign of the work is negative, as it should be for expansion. Work is done on the surroundings by the expanding balloon. So it's working on the surroundings by the expanding balloon.